Yes, Jason, you have a question?
Sir, ask ko lang po, magiging required po ba yung attendance sa synchronous sessions or sa face-to-face discussions?
Okay. Good question, ano? Yung guidelines ng university, particularly sa synchronous sessions, they are optional, no? They are optional. But I highly encourage you to attend the synchronous sessions. Actually, yung experience ko personally with these synchronous sessions is very sad. Medyo malungkot, ano? Because we take the time, kami mga handlers, we take the time to conduct these synchronous sessions, and yet we get very poor attendance in the synchronous sessions. Yung mga estudyante, they have a tendency na umasa lang sa mga pre-provided material, no? or the recordings. When they don't take advantage of being able to interact with the instructor in a live session. There's a lot of value that you get out of interacting with your instructor. So short answer, you are not required to attend, okay? But I highly encourage you to attend. Now, with respect to the face-to-face, I'm already going to tell you this. I'm going to be checking attendance, no? Because I want to have a record of how many of the people in the class are really engaged. No? I just want to have a record. Now, what will I do with this? If it comes to me having to make a decision on a conditional student, I will probably make use of that record. In other words, if I see that a student who is conditional has been very engaged or participates or tries to participate, no, even if maybe cannot answer the question, at least tries, then I'm going to mas magiging magaan yung loob ko dun sa estudyante yun, ano? As opposed to a student that seems not to care at all, no? About attending any synchronous session or any face-to-face session. So I'm not going to take it against anyone if they don't attend the sessions, but I encourage it because I think it's going to help you. And if it gets down to me having to decide on a conditional case, I will take a look at your engagement in the course. Does that answer your question, Jason?
Yes po, sir. Thank you.
Okay. Any other questions? Okay, so let me continue. Okay, so I mentioned that the course is split up into 6 modules. Each module will take 2 weeks. Okay, so the first module that starts today until the end of next week, this is going to be an introduction to semiconductor physics. This is going to be the conceptual part of the course. Some of the concepts here might be difficult for you to appreciate because it is highly theoretical. You'll be glad to know that it used to be a lot more theoretical. When this course was first offered, I guess that was more than 3 years ago, no, the first offering of the course. The treatment of the semiconductor physics part was actually quite deep. So this is already very toned down, no? Yung semiconductor physics na ituturo sa inyo dito sa part na to is already very toned down. It is not quite as deep as it used to be treated, no? But still, some students find difficulty understanding the concepts. I encourage you to take a look again at the material. There's been a lot of material already posted for module 1, no? Semiconductor physics. In fact, here, no? Dito sa module 1, you can take a look. Meron ng study guide. And then there's already notes written up. Semiconductor fundamentals. Okay. There are already notes written up. And the slides used in the recorded videos are already presented here. So this is the official material. I point that out. This is the official material. the things that I will present to you in my synchronous sessions are supplementary material. So let's go back to the course guide. So that's for module 1, that's 2 weeks. And then the 2 weeks after that will be a review of the devices that you took up in 1, 2, 3. No? In EEE 1, 2, 3, these are diodes, BJTs, and MOSFETs. In 1, 2, 3, you took up very simple models of the diode. Okay, but in 131, you're going to take up now a more sophisticated model of the diode. No? This is the Schottky model of the diode, or the exponential model of the diode. And then in 1, 2, 3, when you studied the BJT, it was mostly NPN transistors, and when you studied the MOSFET, it was mostly N-channel MOSFETs. Now you're going to get into PNP transistors. You're going to get into P-channel MOSFETs. You're going to get into transistor biasing, for example, using 2 power supplies rather than a single power supply. So that's in module 2. No? And then in module 2, we're going to continue the discussion of operational amplifiers that was started in module 1. But this time, in addition to discussing or reviewing the ideal op-amp, we're going to take a look at what real op-amps are, and try to provide you with a block-level description of what the inside of an op-amp looks like. No, so this is part of the spiraling curriculum of EEE. No? You learn a little bit more about things as the courses progress. No? So na-introduce na sa inyo yung diode, and transistors. Now it's going to be part of the subject matter again, but in more with more detail, with a lot more detail. Okay, module 3, again, this is 2 weeks. This is BJTs as amplifiers. So we're going to go deeper into BJTs as amplifiers. You're going to learn DC and transient analysis. Okay, and you're going to learn different BJT amplifier topologies. So in 1, 2, 3, you only study the common emitter. Now they're going to introduce the common collector and the common base. And then the same thing for, by the way, after module 3, you have a face-to-face midterm exam. So again, this is something that is different for this semester. The midterm and the final exams are going to be face-to-face. You have no choice. You are going to have to come to campus to take your exam. And we're insisting on this because of the very bad experience we have with conducting remote exams. Actually, very sad what has been happening with students taking remote exams. So this time we're insisting on face-to-face exams. So your midterm exam is going to be November 7, and that is going to cover modules 1, 2, 3. Okay, after that, we continue. So here in module 3, we took up BJT amplifiers. In module 4, we take up MOS amplifiers. So the same thing, DC and transient analysis in the first week, and then the different topologies in the second week. Now in module 5, for amplifiers in general, whether this be BJTs or whether this be MOS amplifiers, you're going to learn how to model these amplifiers in terms of their 2-port network parameters. So the amplifier is going to be a box that is going to be described by a set of parameters. We call them your 2-port network parameters. And it's a way of abstracting the circuit. Instead of having to, for example, place the circuit, or instead of having to, it's in effect, it simplifies the representation of the circuit with a model. A complex circuit can now be simplified by representing it with a model with very few parameters, no, rather than all of the different components in the circuit. So the model which we're going to use is what is called the hybrid pi model. So this is going to be applied to both BJTs and to FET amplifiers. And finally, in module 6, okay, you're going to see how these amplifiers respond to signals of different frequencies. No? So we call this the frequency response of the amplifier. When we have to consider signals of different frequencies, now your capacitors and your inductors are going to be material, because the impedances of your capacitors and inductors are a function of frequency. Okay, so this is where some of the knowledge acquired in 1, 2, 3, especially in the AC analysis part, has to be applied. Okay, after module 6, that's when we will have a face-to-face final exam, tentatively, well, not tentatively, no, scheduled in January 9, and that will cover all modules from modules 1 to 6. But the focus will be from modules 4 to 6. It's impossible to cover only modules 4 to 6 because the material builds on top of each other. So even if we're discussing modules 4, 5, or 6, you will have to build up on what you learned in modules 1, 2, and 3. Okay. 6 modules, 2 weeks each, including your reading break, including the holidays. We anticipate we will be able to finish the course in 14 weeks. That will provide a buffer, no? Magkakaroon ng buffer, maybe a 1-week buffer that we will use for contingency purposes. But even so, we decided that the final exam will be held next year, no, rather than before the holiday break. Okay, in terms of grading, okay, there's going to be 2 bases for your grade. One, of course, would be the midterm and the final exams, and that's going to be 50% of your grade. And the other is your performance in the assessments that will be provided per module. For each module, there will be quizzes that will be administered through UVLE. So you're familiar with these quizzes already from 1, 2, 3. You know, you take it. It's usually timed. The style would depend on the handler. So you have quizzes, and you also have a problem set. For each module, you have a problem set. You will have an opportunity of earning up to 20 points per module for the quizzes and problem sets. Normally, that's half and half, but it really depends on the handler. No, but normally 10 points would be for the quizzes and 10 points would be for the problem set. Every 2 weeks, you're going to have to submit a problem set. Okay. So the total for your quizzes and problem sets, 20 points per module, that would be 120 points. Okay, and that would be the other 50% of your grade. No? So that's your module grade. So it's 50% your module grade and 50% your exam grade. And to pass the course, you need to get a raw average of 60%. No? This is to get a 3. For those of you that fail to take either the midterm or the final, we will be conducting a comprehensive exam at the end of the semester after the finals. This is to give a chance to those with valid reasons, and I note, valid reasons, to replace either their midterm or finals. But the reason should be very, very valid. We will not accept as a reason, for example, the usual reasons students give, no? like they were not, for example, they were not able to study for one reason or another, or they have a cold or whatever. It has to be valid reasons, no? So for us to determine whether your reason is valid or not, you would have to submit evidence. Okay, and whether your reason is valid or not will be discussed in no, among the handlers. No, so it's not going to be my decision alone. It's going to be discussed among the handlers. So there are 4 handlers of the course, as I mentioned. The course coordinator is Dr. Tess De Leon. She's also handling the Wednesday sections. And then there are 2 other lecturers that are handling Saturday sessions. Okay, IZ Bautista and Steven Mindoro. And I'm handling the Thursday sessions. Okay, are there any questions before I go to the first lecture? Yes, Stephen? Yeah, Stephen?
Hindi pa po pala naka-on yung mic ko. Okay.
Okay.
Sir, di ba po yung assessments gagawin sa OVLE?
Yes,
Every kailan po sila ilalabas? Kasi right now po wala pa pong, to my knowledge, wala pa sa OVLE yung first quiz or ano.
Wala pa, no? We commit that the assessments will be available by the 2nd week of the module, no? And then you will be given, after the module ends, you will be given 1 week to do the assessment, no? So we will give you enough time. In other words, hindi kagaya ng 1, 2, 3 na agad-agad due, ano? It's going to, we're going to give you more time, no?
Sige, sir.
Let me go back to that, ano? That's here. Sorry. So for example, no, yung module, anyway, you can take a look at this, ano? Yung module 1 that ends in September 17, no? Ito yung end September 17. That's the end of next week, no? But if you take a look at the problem set, it is due on September 26. No, we made it due Monday and not weekend as before, no. So it's going to be due on September 26. So actually, from the end of module 1 to when it becomes due, you have more than a week, ano. So ganun din dito sa module 2, no. Module 2 ends October 1, but notice it's going to be due October 10. Does that answer your question?
Sir, paano po yung mga quiz?
Yung quiz, that will be up to the handler, ano? But the quizzes probably will be within the 2-week period.
Sige, sir. Okay. Thank you.
I'm not sure, no. It depends also on the handler, but it probably will be within the 2-week period.
Sige, sir.
Any other questions with regard to the course, overall course? Yeah, Julian?
Hello po.
Oh, yeah. Good afternoon.
Yes. Question lang po tungkol sa quizzes. Are we expected to, for all the quizzes face-to-face and online, are we expected to have all the formulas and such memorized, or are we allowed to have a formula sheet?
First of all, the quizzes and the problem sets, these are going to be administered through UVLE, not face-to-face, ano?
Okay.
So, if it's administered remotely, that's actually open everything, no? Open Notes, open Google. In fact, I know that you guys even consult with each other during while you take quizzes, no? Which is quite sad because you're supposed to be doing this as individual activities, but and I hope you don't continue on that practice, because these are again supposed to be individual activities. But we're aware, we're aware that sometimes while you're taking quizzes, you're actually consulting each other, which is not good. But yeah, open notes, open books, lahat, Now the exams, I don't know yet what it's going to be like. Definitely, probably not open book or open notes. But you might be given a cheat sheet. You might be allowed to take a cheat sheet. It depends on the person that makes the exam, actually, or maybe if for example the exam requires a lot of constants to be known, maybe the constants will be given as part of the exam. It really
Okay.
depends. Okay.
Okay, sir.
Any
Thank you
other
po.
questions? Okay, if you have no other questions, I'm going to proceed with a supplementary lecture. So again, the material I already showed you. The material, the official material for the course, it's already published in UVLE for the first week. So this is just something to supplement that, just to give you a flavor of what you're going to be taking up this next 2 weeks. Yes, so this is an introduction to semiconductor physics. Okay, I'm going to start with the structure of an atom. And you learn this actually from high school. You know that an atom has a nucleus. Okay, and then you have electrons that are orbiting around the nucleus. Now, these electrons that orbit around nucleus, they exist in what we call shells. So you have, for example, this. This is a shell. Then you might have another shell. So these are shells. And we know that the electrons orbiting around the nucleus exist in these shells. In these shells. Okay. So your shells are numbered. These are numbered 1, 2, 3, for example. And within each shell, you have what we call orbitals. Within each shell, we have orbitals. What are the different possible orbitals? You have your s orbital, your p orbital, your d orbital, and your f orbital. I'm sure some of you remember this from high school, maybe high school chemistry, yung SPDF. Okay, your s orbital can contain 2 electrons. Your p orbital can contain 6 electrons. your d orbital can contain 10 electrons and your f orbital can contain 14 electrons, no? So these are the electrons that can be contained. And if you take a look at your shell number, no, if you have shell number 1, you only have an s orbital. Okay. If you're shell number 2, you can have an s and a p. Shell number 3, you can have s, p, and d. And finally, shell number 4, you can have s, p, d, and f. Meaning to say, shell number 1, you can have total of 2 electrons. In shell number 2, you have 2 for the s, 6 for the p, so you can have 8 electrons. Okay, and so forth. No, shell number 3, you add another 10 electrons, so that's 18. And in shell number 4, you add another 14 electrons, and that is 32. No? So this is the electrons that can be contained. No? Electrons that can exist. Now we're particularly interested in one element, and that is silicon. Silicon. This is the most commonly used electronic material. Okay, silicon has 14 electrons. Okay, silicon has 14 electrons. If we break down these 14 electrons, how many shells will silicon have? So again, shell number 1, you have 2 s electrons. In shell number 2, you have 2 s electrons. And then you have 6 p electrons. Okay. So this is already 10, no? Now in shell number 3, okay, you have 2 s electrons. However, since 14 lang ang electrons sa silicon, okay, your p now will only have 2p electrons. And you're not going to have any d or f, d subshell in shell number 3, no? Kasi you only have up to the p subshell in shell number 3, because by the time you have the p subshell, you already have all of the electrons in the silicon atom, no? So this is a total of 14 electrons. So take note that for your outermost shell, this is your outermost shell. Okay, you have 8 possible electrons. But only 4 exist. In other words, you have 4 electron states will be empty. Okay. 4 electron states will be empty. So that's the case for silicon. Okay, so we're talking here about individual atoms. What happens when we start to put these atoms together to form a solid? So we're talking here from atom to crystal, no? So this is when we start to put these atoms together to form a solid. Okay, so here, initially, the atoms are very far apart. Okay, and your energy states are very distinct. No? So this is atoms are far apart. So you have distinct energy states. No? When you put the atoms now closer to each other, pag linalapit mo ngayon yung mga atoms, they start having an effect on each other. No? They start having an effect on each other. At some point, your energy states start to split into what are called energy bands. So here we see a splitting into what are called energy bands. So nakikita natin dito, ano? By the way, we're only talking about the outermost shell, and the reason why we're talking about the outermost shell, these are very close to the nucleus. So kahit na malapit yung atoms, no, hindi nito mararamdaman na may malapit pala sa kanya kasi it is very close to the nucleus, no. So it's only the electrons in the outermost shell that will start to interact with each other. So here we see that the discrete energy states start to become what are called energy bands. And the reason for it becoming energy bands is because of what is known as Pauli's exclusion principle. Pauli's exclusion principle. No? Ang sinasabi ng Pauli's exclusion principle, in an electronic system, no two electrons can have exactly the same energy state. So dito, if they are far apart, they don't form a system yet. But when they start interacting with each other, they now form a system, and no two electrons can have exactly the same energy state. And that's why you see the splitting into energy bands, what we call energy bands. Okay. Now, at some point, the energy bands will overlap with each other. Okay, so you see here, no? The 3p splits into bands, the 3s splits into bands. At some point, this is D3, the energy bands overlap with each other. No? But as you put the atoms even closer together, the energy bands again split, no? Split into two bands. And what we're interested in is itong A, this is now the normal distance between atoms in a solid. Itong A na to is the normal distance between atoms in a solid. And you're going to see that the energy bands split again. Okay, we want to focus on, sorry about that. We want to focus on this particular diagram here. What I boxed in red, no? So this is what you call your energy band diagram. This is your energy band diagram. And a blow up of this is actually this on the left, no? So this is actually your energy band diagram. Energy band diagram. Parang inano lang natin, ano? Parang blow up lang natin. So what are your two bands that are shown here, no? The top, you call that your conduction band. And the bottom, this bottom, no, this is at A, no? This is at interatomic distance. You call this your valence bond. There's a gap between your conduction band and your valence band. So this is what we call the band gap. This is your band gap. This is also called sometimes your forbidden energy gap. The reason why you call it your forbidden energy gap is there are no valid energy states for electrons in this particular area. No? You only have valid energy states here in the conduction band and in the valence band. Okay. Now, for semiconductors at well, no, I'm getting ahead of myself, no? So this is the energy band diagram. This is also the energy band diagram. I drew here, or what is drawn here, are the energy band diagrams for 3 different types of material. This is the energy band diagram for an insulator. This is the energy band diagram for a semiconductor. And this is the energy band diagram for a conductor. No? If it is an insulator, itong gap na to is very large. It's about 9 electron volts. 9 electron volts. You might think, is that large? Because one electron is equal to 1.6 times 10 to the minus 19 coulombs. No? So that's actually a very small number. No? This is 1E. 1.6 times 10 to the minus 19 coulombs. So you multiply this by volt. No? So 1 electron volt, I don't like to use red. No? 1 electron volt is actually 1.6 times 10 to the minus 19 joules. Right? Because 1 volt is 1 joule per coulomb. No? So you multiply that by coulomb, you get joules. No? So this is 9 electron volts. So that's 9 times 1.6 times 10 to the minus 19. That's a very, very small energy. But you remember that you have to apply that energy across interatomic distances. And these interatomic distances are very, very small distances. So actually, this is a very large gap with respect to that. Ano? So that is for an insulator. Okay, what is the significance of this gap? Okay. For an electron from here to be promoted here, okay, it has to be imparted this much energy. And this is a very large amount of energy. For that to happen in an insulator, you would have to apply tens of thousands of volts. That is how you can convert an insulator to a conductor. Siguro kung mag-apply ka ng 50,000 volts, magiging conductor yung insulator. No? You have to apply that much voltage. For a semiconductor, the gap is about 1 electron volt. No? So 1.6 times 10 to the minus 19 joules. No? That is the gap. So that at room temperature, there actually are already some electrons here that have been promoted here to the conduction band and now can conduct electricity. No? So this gap is very small in semiconductors. Now, in a conductor, I go back to this. Ano? So in a conductor, hindi pa nag-i-split. No? So for example, dito sa D3, notice na hindi pa nag-i-split yung dalawang bands. In other words, there's an overlap in the bands, no? Dito sa D3. So that's what happens in a conductor. There's an overlap between the valence band and the conduction band, so that there are electrons in the valence band that actually have enough energy to conduct electricity. No? What happens to these electrons? they break away from the original atom and they are no longer associated with the original atom. They now become electrons at large, free to roam around the entire solid. And if you apply an electric field, of course, it will move opposite the direction of the electric field. So that is the difference between an insulator, a semiconductor, and a conductor with respect to the energy band diagram. A semiconductor has, an insulator has a large band gap, a semiconductor has a small band gap, and a conductor has zero band gap. Okay, are there any questions so far? Any questions? None? Are you still awake? I hope. Okay, let me continue. No? Okay. So a semiconductor has a resistivity between an insulator and a conductor. It is generally crystalline in structure. So what do we mean by crystalline? When we say crystalline, ibig sabihin, yung geometric arrangement of the atoms is very regular, no? Has a very regular pattern. No? So this is illustrative of a crystalline structure where if you take a look at the location of the atoms, more particularly the nuclei of the atoms, it is a very regular pattern. No? So that's crystalline. If you have something polycrystalline, then these are composed of chunks of crystals. No? So this is probably crystalline, this is crystalline, but the interface between this and this is not crystalline. No? So there's an interface. And when you talk about an amorphous semiconductor, then that means the arrangement of the atoms in that solid is random. It has no regular pattern. So those are the three types of semiconductors. Now the semiconductors that we'll be taking up in this course will be of this type, no? Itong crystalline. Actually, we're going to refer to polycrystalline in MOSFET, no? Because the gate of a MOSFET is polycrystalline. But the characteristic of a polycrystalline semiconductor is practically the same as a metal. So this is what we will take up in this course, no? In crystalline semiconductors. So the material for crystalline depends on the type. There are three types of semiconductor material. You have elemental, compound, and alloy. Elemental, that means your material is composed of only one element, and that usually belongs to group 4 of the periodic table. So ito. And I already mentioned that silicon is the most commonly used material. In the early days of integrated circuits, it was germanium. Because germanium was much easier to purify and to process at that time. So yung mga unang transistors, for example, unang BJTs were germanium. But later on, when they perfected the processing for silicon, silicon had much better properties. And now 99.9% of all semiconductor devices are composed of silicon. You can also form a semiconductor by combining 3 and 5. So 3, if you combine this and this, usually that results in what we call a compound semiconductor. The very popular compound semiconductor, for example, is gallium arsenide. Maybe the most popular compound semiconductor. So if you take a look, that is this one combined with this one. 3 and combined with 5. Then you also have alloy semiconductors. Alloy, when you say alloy, usually this is combining two metals to form a third type of metal, which has enhanced properties. No, yun yung tinatawag na alloy. But that's not as common as elemental and compound semiconductors. Okay, so I mentioned that the semiconductors we will be studying have a crystalline structure. Okay, if you take a look at the silicon, which we're interested in, that has 4 electrons in its outermost shell. And those 4 electrons form covalent bonds with the valence electrons of the other silicon atoms. So each outermost atom will form a bond with a valence electron of another silicon atom. So if you take a look, this is the crystalline structure of your silicon crystal. The base structure, so this is 3D, the base structure looks like this. Okay, so each base structure has 1, 2, 3, 4, 5. 5. Each base structure has 5 atoms. And so this appears in a regular pattern. And then this just repeats regularly throughout the solid. If you take a look, each atom, for example, this atom will connect to 4 other atoms. No? So you have 1, 2, 3, and 4. No? And that is true for all the atoms here. No? So ito will connect to 4 other 1, 2, 3, and 4. Now it's very hard to take a look at this 3-dimensional. So usually we represent this 2-dimensionally, and this is the 2-dimensional representation. Okay, so this is, for example, this is your silicon atom. Okay, now what does this atom consist of? That consists of this, 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 and this. So this is the silicon atom, and then these are the electrons in its valence bond. Okay, and then you have this naman, ito naman, no? Okay, you have this, and then this, no? So ang pagmimiyari nito, itong apat na to, 1, 2, 3, 4, no? And so forth, no? So you have this, and this, no? Okay, notice that each atom is actually surrounded by 8 electrons. If I take a look at this, for example, so burahin ko na ngayon to, no? If I take a look at this electron, no, it is actually surrounded by 8 atoms, no? Or sorry, the nucleus is actually surrounded by 8 electrons. So the nucleus surrounded by 8 electrons. No? 4 its own, and then the 4 shared with 4 other atoms. Yung 4 sa kanya, yung 4 shared with 4 other atoms. Itong 8 electrons, nakumpleto ngayon yung S at saka yung P. Right? So now I have 3s2 and 3p6. No? So this is 8 electrons. So now I have all my outermost shells occupied. No? Yung 3s2 at saka yung 3p6. Except that, yung 4, inutang ko sa iba. No? Yung 4, inutang ko sa iba. And that is true for each and every atom in the silicon crystal. The 4 electrons in its outermost shell is its own, and then the 4 others are shared with 4 other atoms. And that will complete the s and the p orbitals of the outermost shell. Now, the innermost shell, that doesn't matter because they're too embedded inside. They will not affect the other atoms. No, it's really the outermost shell that interact with the other atoms. Okay, so that is how the solid is formed, and that's why we call it a covalent bond. No, it's a covalent bond. No, because the solid is formed by this sharing of atoms and the completion of the outermost shell through sharing. So the covalent bond is one type of bond. There's another type of bond, the ionic bond, that's not applicable to semiconductors. Are there any questions so far? Any questions? Okay, what happens if one electron in this particular solid, what happens if one electron in this solid manages to gain enough energy so that it is elevated into the conduction band? So, balik tayo rito, no? Remember, these are your electrons in your valence bond. They form covalent bonds, no, in the solid. What if one electron manages to get enough energy para nakatalon siya from the valence band to the conduction band? Ang mangyayari sa kanya, once that happens, no, as illustrated by this, you end up having a free electron here. No? And now, your energy state here becomes empty. Okay, so this becomes a free electron and your energy state here becomes empty. So this, you call this a free electron, and this, we call this a hole. No? And your free electron is no longer associated with the atom to which it originally belonged to. No? So this electron is no longer associated with its original atom. It will now be free to roam around the entire solid. It will have enough energy to roam around the entire solid. And then here we have an empty energy band. You call this a hole. Now, what will happen if I apply an electric field? Okay, so let's say I apply an electric field. Let's say my electric field is this direction. What direction will the electron flow? Along the electric field or opposite the electric field? Can I hear a shout out from someone? What direction will the electron flow? Is it along the electric field or opposite the electric field? Anyone brave enough to give me an answer? Shout out lang nyo.
Along po.
Nice try. If it's not along, it's opposite, no?
Opposite, sir. Opposite.
Yeah, no, it's opposite, no? Because an
Yes,
electric field tends to push positive charges, no? So if you have an electric field, ang ginagawa ng electric field, it tends to push positive charges along its direction. So pag negative charge, it will cause the electron to flow opposite the electric field, no? So ang mangyayari dito sa electron na to, okay, this electron will flow this way. Okay. Now, what will happen to this hole? No? What will happen to this hole? For example, itong electron na to, so this electron that I'm pointing to, does not have enough energy to go to the conduction band. It does not have enough energy to go to the conduction band, no? But it might have enough energy to go to this hole over here, to occupy this energy state over here, no? So posibleng mangyari 'yon, no? So itong electron na to posibleng tatalon dito. So pag nangyari 'yon, buo ngayon tong covalent bond na to, mabubuo. Pero ito ngayon yung magkakaroon ng butas. And this is going to be your new hole, no? This is going to be your new hole. Now, kung meron akong bagong hole dito, the same thing can happen, ano? Itong electron na to may not have enough energy to go to the conduction band, but might have enough energy to occupy now this hole, no? So pwedeng ganun uli, ano? And then now this is your new hole. So una, nandito yung hole. Okay? With the electric field, nandito ngayon yung hole. And then later on, nandito ngayon yung hole. So pag tinignan mo, the hole looks like it is flowing along the direction of the electric field. Excuse me. Okay, the hole looks like it is flowing along the direction of the electric field. So there are two things now that are moving. No? One thing that is moving is the original electron that caused the first hole, which is already in the conduction band. And then the second thing that is moving is the hole. No? Actually, it's not really the hole moving, but it is electrons in the valence band occupying the hole, moving in the direction opposite the electric field. No? So the hole looks like it's moving toward in the same direction as the electric field. So when an electron breaks loose, you have two charge carriers. Your two charge carriers are your electron and your hole. Right? Now when you have a pure semiconductor that is pure silicon, for example, you call this an intrinsic semiconductor. At 0 degrees Kelvin, or absolute zero, this behaves like an insulator. All the valence bands, all the valence electrons are occupied, no? All the valence energy levels are occupied. There are no free electrons and no holes. That is in a pure semiconductor at 0 degrees Kelvin. There's like an insulator. Kasi walang electrons na nasa conduction band. But at higher temperature, the valence electrons can gain enough energy. You call it thermal energy, energy absorbed from from temperature to break away from its covalent bond. It will be now elevated, promoted to the conduction band, and then you form now a free electron and a hole. You call that an electron-hole pair. And both the electron and the hole can contribute to current flow. So I'll just provide here some definitions. So if N is the number of, this is free electrons, no? Number of conduction electrons per centimeter cube, and P is the number of holes per centimeter cube. First of all, in a pure semiconductor, N and P are equal. Because for every electron that breaks away, a hole will be created. No? So N is the number of conduction electrons per centimeter cube. P is the number of holes per centimeter cube. And in a pure semiconductor, N will be equal to P. Now we have what we define as the intrinsic carrier concentration. The intrinsic carrier concentration is the number of conduction electrons that exist in a pure semiconductor or an intrinsic semiconductor at a particular temperature. And there was a formula developed for this. This is a formula that you don't have to memorize. In fact, you don't have to know. I just present it here for completeness. So this is the formula that was developed for intrinsic concentration. Okay. It depends on the material. Like for silicon, this is the value for silicon. It depends on the band gap. The band gap, this is the difference between EC and EV. I forgot, by the way, I forgot to define what EC and EV was. Ano? Depends on the band gap. This is the forbidden band. And it depends on Boltzmann's constant. This is the Boltzmann's constant relates temperature with energy, no, for particles. And if you compute for Ni, for silicon, it's approximately 1 times 10 to the 10 centimeters cube at room temperature. In other words, you're going to find, at room temperature, you're going to find 10 to the 10 free electrons per cubic centimeter in a pure semiconductor. Now you might say, is that big? Actually, if you consider that silicon has 5 times 10 to the 22 atoms per cubic centimeter, and it's only 1 times 10 to the 10 that creates a free electron. Only 1 times 10 to the 10 of these atoms create a free electron. Okay, that's for every for every 1/5 of 10 to the 12 atoms, you only have 1 free electron created. For every 1/5 of 10 to the 12 atoms, you only have 1 free electron created. So actually, it's quite a small number compared to the total number of atoms per centimeter cube. Now, this is what you call the intrinsic concentration. And that is dependent on temperature. So that is shown by this graph. So this is the graph for silicon. At absolute 0 or 0 degrees Kelvin, you don't have any free electrons. Your material is like an insulator. At room temperature, this is about room temperature, 300 degrees Kelvin, room temperature. It's about 1 times 10 to the 10, and that's for silicon. And as you increase the temperature, your intrinsic concentration becomes higher. Germanium, it's a bit higher. This is for gallium arsenide. And this is for gallium phosphate, another compound semiconductor, gallium phosphate. So that's just to give you an idea of how your intrinsic concentration varies with temperature. So that's all I wanted to discuss today. No, I forgot to define something earlier. No, dito no. There are two energies that we're interested in. That's EC and EV. No? EC. Okay. EC is the smallest energy that a conducting electron can possess. No? Yun yung ibig sabihin ng EC. It's the smallest energy that a conducting electron can possess. And EV is the largest energy a bound electron will have. No? Possess also. No? Therefore, for a bound electron or a valence electron to promote to the conduction band, the minimum energy that you have to give it will be your band gap, EG, and EG is equal to EC minus EV. That is your band gap. Okay, so that's all I wanted to discuss. So please take a look at the material that is posted in UVLE. No. And we'll continue with the with the subject matter on Thursday. Are there any questions? Again, with respect to what I presented and with respect to the course policies, any questions? Okay, so that's all. May question, ano? Joel, the rest of you that don't have any questions, no, if you have something else to do, it's okay if you leave the meeting. I will close the session as soon as everybody leaves, so that anybody that wants to ask a question can still do as long as I'm here. No, was there a hand raised earlier? Was that Joel? Yes, Joel.
Yes po sir. Everyone po yung synchronous natin.
I'll for now, no. I'll follow the schedule of the course. So that would be Thursdays from 2:30. Pero pag nagkaroon ng face-to-face, I might discuss with you finding a common time with my other section, depending on how many indicate their their commitment to attend the face-to-face sessions regularly.
Okay po.
Okay.
Sir.
But
Thank you po.
as of now, as long as I get this kind of attendance, I can conduct separate sessions for my two sessions, no. But if it I hope it does not happen, no. Kasi ang experience ko talaga nagdidwindle yung attendance. I hope it does not happen. But if that starts to happen, I might ask, no, that we just combine into a single session.
Okay po sir. Thank you so
Okay.
much po.
Yeah, you're welcome. Yeah, I'll leave as soon as the last person leaves, no, so that you can, anyone that wants to ask a question, you can.
Thank you po, sir.
You're welcome.
Thank you, sir.
Welcome. You're welcome.
Thank you po, sir.
Thank you po,
Okay.
sir.
Thank you
Thank you,
po.
sir.
Have a nice
Thank
day
you, Prof.
po.
Sir, mapopost po sa UVLE yung presentation kanina.
Yeah, I'll post it, no.
Okay po. Thank you po,
Okay.
sir. Bye po.